Hello. Yeah, can you hear me?
Yes, we can
Yes,
hear
sir.
you.
Yes,
Okay.
sir.
Okay, good morning, everyone.
Good morning, sir.
Morning, sir.
Morning. Yeah. So, after a week, right?
Yes.
Hmm. Okay. Anyone who has joined afresh? Anyone who has joined uh, afresh in the sense that it's his first class? Vikram. Okay. Okay. Fine, Vikram. So, you'll have to catch up a bit. So, let's start uh, today's session. Okay. So, just to review as to what we did in the last session. So we were trying to so we now know that statistics actually is the basis for all machine learning and data science, wherein we studied that statistics actually is starts from the collection of the data and then analysis of the data. Uh, so collection is again a task which needs to be so data normally at times it could be available with the companies or organizations, but most of the time if there's a problem statement which you have made, or if there's a new problem statement, it's possible it's the aggregate data may not be available, right? Or at times it's you also require to do some survey or some so there are different types of surveys which are done uh, to to aggregate the data, right? And once you have aggregated the data, obviously the uh, uh, objective is to then maybe see how we analyze the data before we uh, use that data for machine learning purpose or any analysis purpose, right? Even even for a minimum analysis purpose, like say maybe finding a mean also. So probably if there are some uh, values which are not there in the data, right? Suppose you have captured the height data of 100 people, and there are about 20 people who have not mentioned that data, right? Now, wherein obviously you have to ensure that how do you handle that missing values? How do you handle that missing values, right? How do you replace those missing values? You delete those missing values, or you replace it with some value which is more true to the data, right? So to that extent, we started looking at the data, and we saw that so data types, essentially we started with data types, wherein we said that there are two types of data. There is a quantitative data and there is a qualitative data. Quantitative data can be divided into ways. One is discrete and the other is continuous. And then we saw that categorical data or qualitative data can be divided into two ways. One is nominal and one is ordinal, right? And then we saw given a data set, we can identify a independent variable and a dependent variable based on the problem statement, right? And then we saw that there are three types of analysis which can be done essentially, namely univariate analysis, bivariate analysis, and multivariate analysis. So essentially, uni means one variable analysis. That means we are focusing on one column of the data set. It could be a categorical data or it could be a numerical data. And if it's bivariate, then we are saying that we are looking at two columns at a time, and we can analyze two columns at a time. And then third is multivariate, wherein we are analyzing more than two columns at a time, and it could be a combination of a numerical data or a categorical data, right? And we also saw that in terms of analysis of a single column, we can have we can look at a mean of the column. We can look at the median of the column, which is a central value after sorting the data. Mean is simply the central value which we get by adding all the terms and dividing it by the number of items that column has or that data series has. And mode is the data which relates to the most frequent data in the data set, most the frequency of the highest frequency. And it is possible that a data set is bimodal, which means that there are two modes in the data, and it's possible that there is no mode in the data as well, because if all the data items have the same frequency, then there's all are highest or all are the same, so there's no mode, in which case. Then we saw the other way of looking at the data is how do you see the dispersion, that means spread of the data, how the data is spread. If that is something which you have to look at. So then you look at something like range, which gives you the difference between the maximum highest item in the data, and the difference between the highest item and the lowest item in the data. Then we saw something called interquartile range. We said this relates to median, wherein so if we can look at the data from the perspective of what is the data at the 50th position, what is the data at the 75th position, what is the data at 25th position, right? Once we sort the data, and if we find the difference between the 75th position and 25th position, this again gives you some sense of range, which is called interquartile range, right? 75th position is called Q3, 25th position is called Q1, and 50th position, which is median, is called Q2. And then we said that there's another way of looking at data. Another term which we saw was variance, which wherein we we see how the data from the average, how the data is spread from the average of that data. And this gives us the spread of the data, which essentially means if you calculate variance mathematically between two different series of data, then whichever data gives you the higher variance would mean that the data is more spread out. That means there's more gap between respective numbers. And if there is, in the other case, if the variance is less, which means that there is less gap. So data is more compact or more near to each other. And we said that square root of variance, so whatever value of variance comes, if we figure out the square root of that, that gives us standard deviation. And then we said there are other matrices like measures of shape. So measures of shape comes from, we said, then we got into the distribution of the data, right? We saw the distribution. So distribution essentially is defined as a frequency. Distribution is what? Distribution of the, say, if a set of numbers are given, distribution means that, in which case what we do, we create different bins and put the respective numbers in the respective bins. And whatever is the frequency of that particular bin, that becomes the uh, distribution, histogram. And we said your histogram can look like, if you plot a histogram for the data, it can give you three different types of shapes. Okay. It can give you three different types of shapes. One is a uniform shape. That means it has an equal distribution around the center, which is mean. In such a type of data, mean is equal to median is equal to mode. So if you calculate these three parameters, it will come out to be same for that particular data series. And it's possible that the data, your data, the way you plot, when you plot the distribution, your histogram looks like this, wherein there's a right tail, the tail on the right side, right? So whenever there's a tail on the right side, it is called a positive skew, and whenever there's a tail in the left side, it's called a negative skew, right? Now, for example, we can also calculate skew mathematically, wherein it will have value between, if it has a value between plus 0.5 and minus 0.5, it's called symmetric. If it has a value between 0.5 and 1, and correspondingly minus 0.5 and minus 1, then it is moderately skewed. And if it is positive 1 and minus 1, if it is more than plus 1 and more than -1, then it is highly skewed. Now, just to share the example with you, so if we say income of individuals is mostly skewed. So, do you agree with this? Can somebody explain that? What is that? If I say that income of individuals, so if you take the income of maybe people around you, or then then we say that it is right skewed. So does it? Do you agree with this? Can you explain this to me? Hi. You can hear me, right?
Yes, sir. Right skewed.
Okay.
Yes, sir.
Okay. So if I'm saying it's the right skewed, then what is that comes to your mind? What is the so what would mean? So if I take 100 people around me, or maybe full Mumbai for that matter. So how do you think income would be spread?
Right skewed
There'll
because
be
less number
yes,
of people will have more wealth, so the graph
yes,
initially would be very
yes,
high.
yes, yes. As you move right, that means you yeah, yeah. So 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 there are very few people who would have high income, right? And there would be very large number of people who will have less income. Is that sense? So on the x-axis we are showing the number of people, right? On the x-axis we are showing number of people. On the y-axis we are showing the frequency of their okay, or we show the income on the okay, very large income. No. So essentially, what we are saying here is that there will be large number of people who would have the less salary, right? So maybe if I say my mean salary is say 25,000 rupees, then if my salary increases, there will be very few people who will have the high salary than say 25. As the salary increases, okay. So let me correct. So on the x-axis we are taking the salary, okay. So and if I say my mean salary is say 50,000 rupees, then as my salary increases, the number of people in that salary bracket increases. As my salary is less than 50,000, is it correct? Is it clear now? Yeah. So is it clear? Please respond. See, assuming I have a salary bracket of 10,000 to 20,000, 20,000 to 30,000, 30,000 to 40,000, 40,000 to 50,000, 50,000 to 60,000, 60,000 to 70,000, right? So how will it look like? So say 60 to 70,000, there will be 10 people, right? 70 to 100,000, there will be 5 people. At 40 to 50,000 level, there could be 15 people. Is it? Yeah, I'm expecting your response, please, on this. Hi, am I audible to you? Yeah. Okay. So is it clear? Is it clear to you that I'm saying that income of individual is mostly right skewed? Okay. Okay. Now, the other statement I'm making is height of people will be normally distributed. So given a class, right? Given a class, people, and we measure their heights, right? So and we'll find that okay. So most of the so if median height, so if median height is coming out to be say 6 feet, for example, then on the there will be then say there will be very so as we go on the right we are if this is 50 if this is 6 feet, if your median is 6 feet, then 6, 7, 8, 9, right on the right side. So as we move towards the right, there will be less number of people on the who will have the high height. There will be hardly anyone who will have a 6, 7 feet height, right? So as we go on the right, the number of people decreases. The number of people in that. Similarly, if we go down, so there will be a person who will be 5 feet, 4 feet, 3 feet, right? There will be hardly anyone who will be maybe less than 4 feet. So what happens is that most of the data, so most of the data, the frequency of the data decreases. So this is the normal. This is what we call normal distribution. So whenever any phenomena behaves like this, wherein it is uniformly distributed around mean, and it decreases as we go far from mean, right? So there will be very few extreme values in that data. That sort of distribution is called normal distribution. So usually performance of the people, performance of the performance of the machines is that who would have a very high performance, right? Who will have a very high performance. There will be very few people who will have a very bad performance. Most of the people will have the performance which is around the mean. They'll have average performance, right? Now and the left skewed. Now the left skewed. So class grades is usually left skewed, which means if it's an easy exam, right? If an easy exam is given, most of the students will score more than 60 or 70, right? There will be very few who will score very less marks. So if I say average is say 60, right? So as we go on the right, so most of the students have scored more than 60, or maybe if I say average is 50, then most of the students who have scored is because the exam is easy, so most of the people have scored well beyond 50, 60. So most of the students will lie at the right side of the graph of the mean, and there are very few people who are on the left side of the graph, right? So this becomes a left skewed. This becomes a left skewed. And I also told you that usually whenever we do analysis of the data, whenever we do machine learning on the data, we our objective is that our data should be normally distributed. Our data should be normally distributed. And whenever the data is not normally distributed, we have to transform the data. We are required to transform the data so that it becomes normally distributed, right? And there are mathematical ways of doing it. So this is what is called transformation of data, and so usually there are techniques to transform the data to make. So if data is your skewed data, then you have to make it uniform, normally distribution data. Then you either use the logarithmic. So you transform all the values to its logarithmic values and then process it, right? So you take the logarithm of all the data which you have of that column of the data wherever you find skew, you'll find that it gets converted into a uniform. It gets converted into a normal distribution. The other two methods are so you find the square root. If you take the square root of those observations, right, then that becomes a then that tends to become a normal distribution. And the other is that we take the inverse. We take 1 over the data. We just inverse that data, and that is one of the ways. I'm not sure whether you applied it or not, but whenever you do machine learning, try and do this, find a skew of the variables, and then normalize it by using one of these methods. So logarithmic, square root, or inverse. So these are the three methods which you use to convert to remove the skewness in the data. Okay. Okay. The other term which other parameter which we shape is kurtosis. Kurtosis. So this again comes from the histogram or distribution of the data which we plot. And now, so there are three types of kurtosis which is possible, wherein if you find that it's a very high peak, so then that is called leptokurtic. If it is a medium peak, then it is mesokurtic. And if it is a flat, so it tends to be more flatter, then it's called platykurtic. And if we mathematically calculate this kurtosis, then we can have three types of, so there are three uh, types of kurtosis can be defined by three different values. So if k is around 3, if that value of kurtosis is around 3, then it is called mesokurtic. If k is greater than 3, then it is platykurtic, and k is less than 3 is leptokurtic. Okay. Okay. Now let's get into some visualizations which we the revision as to what different types of visualizations are, and how are they linked to what we are doing. So, so histogram. Can anyone tell me now what is histogram? What is histogram? What does histogram show you?
Frequency distribution, sir.
Yeah, it's a frequency distribution, right? Okay. And so histogram is what type of analysis? Univariate, bivariate, or multivariate?
Bivariate.
Histogram is what? Think again.
Univariate, sir.
Uni.
Yeah. Is it clear now? So it's a univariate because it's so given a height of the students or weight of the students, right? Given one numerical column, you can plot a histogram. You don't need two columns to plot a histogram. Okay. So essentially, univariate means when we are looking at only one column. So whatever we can do, so mean we can find only for one column. Mode we can find only for one column. Variance we can find only for one column. Are you with me on this?
Yes, sir.
हाँ, so histogram is a univariate analysis. Histogram अगर आपको काफी सारी हाइट्स दी हैं, आप उनसे उनकी उसमें क्या फाइंड करोगे कि किस हाइट में कितनी फ्रीक्वेंसी है, राइट? 5 फुट के कितने लोग हैं, 6 फुट के कितने लोग हैं, 4 फुट के कितने लोग हैं, राइट? So that frequency, so you need only one. So histogram is a univariate. Okay. Box plot. Are you familiar with box plot? Do you know what a box plot is? You can let me know or chat if. Okay. 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 No, box plot is again. So box plot can be box plot can be a univariate, and box plot can be bivariate or multivariate also, right? So let's look at box plot. So box plot. See, so if I have to plot the median, we have to plot the median of the data, right? Then we use box plot. If I have to look at the median of the data, then we plot box plot. Okay. So if you plot, I'll show you the demo also in the later half. But as of now, if we draw a box plot of any column, say height, for example, then what is median? What is median? What is median?
Middlemost observation.
Middle value, right? After we segregate, after we
After
sort the
sorting
data,
the
right?
data. Yes.
Yeah. So okay, so this box plot will look like this. It will be a box. It looks like a box, right? It could be a horizontal box or it can be a vertical box. The central value, it'll give you the central value. It will give you the central value, which is called the median, right? Which is called the median. And then the upper value, this level, the upper level of that particular box plot would give you the position of the 75th value, 75th position value, and then the lowest gives you 25th position value. So Q1, Q2, and Q3. So if you are able to draw a box plot, we will be able to tell what is the Q1 position, what is the Q 2 position, and what is the Q3 position. Right. Then we also get, and this is the lower limit of that data. Then there is, and interquartile range is what? Difference of Q3 and Q1. So this difference between Q3 and Q1 gives you the range. This is called interquartile range, right? And then there is also concept of outlier. So outlier, there's also concept of outlier. So outlier would mean any data which is lying beyond a particular level, right? Beyond a particular level. Okay. So usually we, whenever we come across any data, say I give you the data of, say, uh, salary of people. So I say data is 50, 55,000, 56,000, 57,000, 58,000, 59,000, and then 5 lakh, 10 lakh. So what do you think is the outlier in this? What is the outlier? Okay, so I've given an example. I'm saying that there's a data set of salaries, and the data looks like this: 50,000, 55,000, 56,000, 58,000, 59,000, 75,000, 1 lakh, 5 lakh, 10 lakh. Do you, so if I, so do you, what is the outlier to this data?
10 lakhs.
10 lakhs.
Yeah. 5 lakhs or 10 lakhs becomes a outlier, because it's two. So outlier would mean two extreme values, very extreme values. And how that does that? How do we calculate that extreme value? There's a mathematical way to do that. So the way is, okay. So at the top, at a higher level, we take this 75th position value, right? We take the number at the 75th position and add 1.5 times interquartile range to that, right? And add 1.5 times interquartile range to that. We'll get a number. Now that number is called outlier. That number will be called outlier. So whenever we are asked to find a outlier mathematically, because that is the way we have to, we should do, because otherwise, if the data is not very differentiated enough, in the sense that the way I told you, then you have to calculate it mathematically. And how do you calculate that outlier? You take the 75th position data point, and add it, 1.5 times interquartile range, 1.5 times interquartile range, and then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1.5 times interquartile range to that. And then add 1 add 1.5 times on the negative side, on the lower side. On the lower side, we take 25. We take this 25% position number, right? And minus, because we have to go on the minus this direction. So minus 1.5 into range, right? And we'll get some number beyond this low limit, and that is what is called what will be called a outlier. So the outliers can be on the positive side of the data, and outliers can be on the negative side of the data. Okay, is that clear?
Yes, sir.
Okay. Okay, so box plot. So box plot is drawn for a single variable. I've told you it's for a single variable, and uh, uh, this it is drawn whenever we want to understand the median of the data, right? Whenever we want to understand the median of the data. Now, the same box plot can be used to understand the medians of multiple. So, okay, for example, so this box plot can also be drawn to look at a bivariate analysis to two columns. So, if you have to look at two columns data, analyze two columns, then we can use box plot. So, in which case, one column should be a categorical data, and the other should be numerical data. Okay, I'll explain, Satyam. Uh, 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 okay, so let me come explain multi bivariate analysis or multivariate analysis in a box plot. So assuming, so let's go back to the data then. Okay, now suppose, so I said we have to create a multiple say bivariate data we have to look at. So suppose, I look at two columns, gender and lung cap, right? Gender and lung cap. And now if so one is that I can create a box plot for lung cap directly, and it will give me the median value. It will give me the it will give me Q1, Q2, Q3. It will also show me outlier, right? Because the cross, it will show, if it automatically show, so you don't need to calculate. So when you draw a box plot, if there is a outlier in the data, it will show you. It will show you that, and it will also show you the the upper limit of the data and the lower limit of the data, and beyond that the outlier, right? Beyond that the outlier. Uh, and okay, so this is one. So you can actually see lung cap, and you can do it for height, you can do it for age. Now, if you have to look at gender and lung cap both, right? Now, it is possible that you see the median for male and see the median for female, right? Now, you can draw two box plots for this data, gender and lung cap, wherein you are plotting the median for the male versus lung cap, and you're plotting female versus lung cap. In which case, you will get two box plots, which will show you that the median value of the uh, uh, male versus lung cap and female versus lung cap. Is that clear?
Yes, sir.
So that becomes a bivariate use of a there are only two categories. If there are say 5 categories in this, right? Then you can actually see it for 5 categories. Yeah, is that clear? So that become 5 categories as well. So box plot, you can draw, so there will be multiple box plots which will be plotted for each of the category separately. But this remains a bivariate analysis, right? This doesn't become a multivariate. Are you with me on this? So I'm saying box plot is a bivariate because we are still looking at two columns only, right? One is the categorical and one is the numerical. So it's must. If you have to plot a box plot, one column has to be categorical, the other column has to be numerical. In the categorical column, you can have multiple categories, not necessarily two, right? You can have 5 categories in the, you can have 10 categories in the say, in the categorical column, right? Each category will have a different box plot. But end of the day, we are still looking at 2 columns only. Are you with me on this?
Yes, sir.
Yeah. Okay. So it still remains a bivariate plot, right? So is it clear to everyone? So
Yes, sir.
yeah. So whisker is just this area. So whisker is the, so when we'll plot box plot, we'll see what is happening. Just hang on. Yeah. Okay. Very- Yeah. Yeah. Okay. When we, so just to come back to this, okay. So this part, so you will get a box, you will get a central line, you will get a outlier if it is there, and you will get a whisker like this. This T shape is called a whisker. This T shape is called a whisker. Okay. And anything beyond this T shape is an outlier.
Oh, how we will calculate it?
Pardon me.
How we will
This,
calculate whisker?
see, it will calculate itself. So whisker
Sorry, could you
we
come
don't
again, sir?
calculate. Whisker it automatically. So if we draw so whisker we don't draw whisker. It automatically gives you the whisker. So this is a maximum. This is the maximum value. So upper limit is the maximum value before the outlier, and lower limit is the minimum value of the data before the outlier.
So outlier goes beyond 75% plus 1. Plus
5. It will
1.5
go
value, right?
beyond this whisker. It
Okay.
will
Okay.
go
Okay.
beyond this upper limit, the maximum
Okay.
value. Okay,
Sure.
and it will go beyond this lower limit.
Yeah. Got it, sir.
Okay.
Okay. Thank you, sir.
So whatever resides beyond this becomes a outlier.
Okay, sir.
So, and this upper limit is essentially a maximum number in the data which is before the outlier, and the lower limit is a minimum minimum value of the data in the data set in the data series before the outlier. Yeah. Okay. Then okay. Then we have this bar chart which you are mostly familiar with, wherein, so if I have so again this is a, so bar chart is again possible only if we have one categorical data. This is again a bivariate plot. Bar chart is a bivariate plot wherein it is wherein say we have the yearly sales data, right? 2001, 2002, 2003, and some sales value, right? Then we plot. Then what we do? Then we can create a bar plot of that, wherein each category is distinctly shown. So that is why you find a gap, right? That is fine. That is why you find a gap between these. So 2001, 2002, 2003, 2004, and the respective sales amount. So even for a bar chart, it's a variate analysis wherein you have one category and one numeric column. Okay, say population of different cities if you want to plot. Okay. Then comes the next thing, which is line chart. Now line chart is typically so usually drawn, line chart is usually drawn whenever you have time series data. Time series data. Time series data would mean that one column of the data is a time, and the other part of the data is say stock rate. Right? They have two columns, year and say inflation rate, for example, right? So, and in which case you can draw a line chart. You can draw a bar chart also. You can draw a line chart also. That's one and the same thing, right? But usually line chart is normally used whenever we have to look at a time series data. And when I say time series data, which essentially means that there are two columns in the data, wherein one column is essentially time. Time could be in terms of years, in terms of months, or in terms of seconds. So usually stock data, right? Usually stock data, stock share price data, you will find in time series data. Inflation rate, weather maps, usually everything whatever is linked is seen with respect to time. So is a company's sales data time series data? If I say, can you give
Yes, sir.
me, okay, so can you give me any other example for time series data?
Population.
Yeah. So it depends, right? Population with respect to time. So if you are looking at population, say 1950, 1960, and then, but you can also look at a population with respect to say city-wise, right? Bombay, Delhi, Calcutta, right? When you are
Yes.
plotting population with respect to the cities, then it's preferable to make a bar chart, right? And whenever you are looking at it with respect to time, for example, say yearly data,
I
then
said with respect to years, sir.
pardon me.
With respect to years.
Yeah. Yes, years or time. The denomination can be anything. It could be microseconds. Say for life of a say virus or life of a bacteria, right? It could be nanoseconds to say millions of years. Okay. Pie chart is again the typical thing about pie chart is that it always shows you the percentage. So pie chart is always showing you the percentage pie of that particular category uh, against the whole, which is 360 degree, right? So for example, if any person has an investment portfolio wherein he has spent stock in stocks, bonds, CD, and savings, and these are the respective amounts which he has spent. Now, if we create, so if you have to create a pie chart, we'll have to convert those values into percentage, right? We pie chart converts those values into percentage. So if I have these two columns, investment type, that means again this is a categorical column, and this is a numerical column, and I'm plotting these two variables. Then if I draw pie chart, it will automatically show me the percentage. It will automatically show me the percentage. Okay, is that clear? And the size of the pie is corresponding to the percentage of that particular value as a percentage of the whole, as a percentage of the whole. Clear? So again, this becomes a bivariate chart and a bivariate analysis. Okay. Ogive is actually, so just to, okay. So let's look at this example wherein we are saying that these are the of by different students, 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60. These are the bins and we are saying that there are three people who have got the numbers between 10 and 20, and six people between 20 and 30, and there are total 20 people, right? Now if okay, now if we draw so given this class and frequency, what is that you can draw?
Histogram.
Yeah. Okay. Great. So but if we have to, so okay, now there is another term called relative frequency, right? Relative frequency. So there's a frequency is one term, right? Frequency. Then if I say relative frequency, that means 3 with respect to 20, which gives me the relative frequency.
So your
And
voice is
if I,
breaking, sir.
so this is a relative frequency. Okay. I think it is internet. Okay, is it okay now or?
Yeah, it's audible. Would you repeat the last sentence again?
So you got till this class and frequency plotting, and somebody said histogram, right? You're you're clear to that point, up to that point.
Would you repeat it once again?
Pardon me?
Would you repeat it once again?
Okay, so what I'm saying is in this, so you're able to see this table, right? Class,
Yes,
so
yes, yes,
and frequency, right? So
yes.
I asked, so if you have to plot this class and frequency, what would be the type of graph which you would make?
Histogram.
Yeah, right. So this is one. Now the other time which I am explaining is relative frequency. There is a frequency, and then there is a relative frequency. So relative frequency would mean that what is the frequency as compared to the whole, right? As compared to the whole. So 3 divided by 20, 6 divided by 20, 5 divided by 20 gives you the relative frequency. Okay. Then there is a concept of cumulative frequency. Cumulative frequency. Now, cumulative frequency, how do we get it? So we get 3 here, right? 3 from 3. Then 3 plus 6, 9. 6, 3, 9 plus 5, 14. 14 plus 4, 18. 18 plus 2, 20. So from the frequency table, we can draw cumulative frequency by adding the respective values, right? By adding the respective values in the next column. Okay. So how does cumulative frequency help? So if I have to ask you, how many people are there? How many? How many? Okay. So my question is, how many people? How many students have got marks less than 30? How many students have got marks less than 30? So what would be the answer?
9.
9 straight away, right? So this is the cumulative frequency. If I ask you what is the how many people have got uh, more than 50, for example, sorry, less than 50.
80.
Yeah.
18,
So this is advantage of, so this is what cumulative frequency gives you. Frequency gives you just the frequency of different categories or classes, and cumulative frequency gives you the straight away the less than or greater than value for at a particular level. And so like there's a relative frequency, there's a cumulative relative frequency also, right? There's a cumulative relative frequency also, wherein you add, say, 0.15 is a relative frequency at in the first row, then you add 1.15 plus 0.13, it gives you the point. It gives you 0.45, which is a relative frequency of row 2, and likewise. Now, ogive is a cumulative relative frequency table. Ogive is a cumulative relative frequency table. Okay, just make a note of this, and it straight away gives you the trend of the classes. It gives you the trend of the classes, right? Okay. So Ogive is a cumulative relative frequency table. Again, it is a it is a sort of, it is a single, it is a univariate, right? Ogive is a univariate, right? Are you with me on this? It's a univariate analysis.
Yes, sir.
Yeah, Ogive is a univariate analysis, right? You're deriving this information from this data, one series of data like this, which is given here. Right? All this is being done on only on one series of data, right? You determine the frequency of that, you become determining relative frequency of that, and you're then determining the cumulative relative frequency of that. Okay. We'll come to scatter diagram later. Okay, fine. So just to, since we are anyway doing by variate analysis here, okay. Now, this scatter diagram is also a bivariate analysis, right? But the typical, but you have to note that scatter diagram can only be drawn for two numerical variables, for two numerical variable category, right? We can't draw such scatter diagram for say one category or one numerical, right? And we can't draw scatter diagram if both are categorical. Okay, so scatter diagram is always linked to two columns which are numerical in nature, which have to be numerical. Say something, say volume per day and cost per day, right? Wherein you take one as x-axis and one as y-axis, and you get a plots. You get a plot like this, right? Now this okay. Now there are two things. Whenever we do the two numerical plotting, we get we get to we can derive two information out of from this. One is that the direction of the trend, direction of the data, right? Now this direction, now here the direction is positive. Here the direction is positive because so as I move from 20 to 30 and 30 to 40, my value on also. So for example, 20 I have the value of say 125. For 30 we have the value of say 150, right? So what I am observing in this data plot is that as I am moving right, as I am moving towards the right, my y is also moving upwards, and in which case it will give me the direction like this, direction positive trend. It's a positive trend, right? And if the data if the data is plotted like this, let me see, like this, right? Then it becomes a, then what we are seeing is that as we are moving from left to right, the data point is decreasing. The data value, the y-axis is decreasing, right? As I'm moving from uh, from left to right, my I'm moving from top to down, right? So this becomes a negative direction. This becomes a negative direction. So this is a negative trend. Okay. Now uh, okay. So one is that I said scatter diagram for two columns, two numerical columns, right? Now these two numerical columns, I can have derive two values out of it, two values like two parameters out of it. One is covariance, the other is correlation, right? The covariance and the correlation. Okay, covariance would mean what? The variance between two columns. Covariance means variance, and we know variance, right? We know variance. Variance essentially is the spread. Now here covariance is always between two columns which are numerical, and covariance tells you just this direction. It just tells you whether, if I find the covariance of this, right? If I find the covariance of this data, it will just give me whether it's a positive direction or a negative direction. Okay, covariance just gives us whether it's a positive direction or the negative direction. Okay. And correlation tells us the strength of that positiveness or strength of that negativeness. Okay, correlation tells us the strength of that direction, right? Or how closely the data is packed for that direction, right? How closely the data is packed for that direction. This is what is called correlation. Okay, covariance and correlation. These are two different terms. Though if you draw a scatter diagram, you are able to find out the both. If you draw a scatter diagram, you are able to find out the direction of the data also, the direction of trend also. That means if one is increasing, other is increasing, or if one is increasing, other is decreasing, or there is no pattern, there is no fixed pattern, right? Then there is no fixed pattern. So it could be decreasing, increasing, decreasing, increasing. Then that is no correlation, no covariance, right? Sort of situation. So let me. Okay. So let me. So we have covered this bit. Side. Okay. Now there. So a bar chart, right? A bar chart can be a stacked bar chart as well. So let me tell you what stacked bar chart would mean. So stacked bar chart becomes a multivariate. Okay. So let's. Okay, so I'm at bar chart now, right? So wherein I said that if it is so say for example, list of cities on the x-axis and the population on the y-axis, then we are showing that what is the value of population at each city, right? Now wherein can also to see the population gender wise, right, in each of these uh, okay, if I have to see the one variable. So I'm saying if I say a stacked bar chart, then it becomes a multivariate. It becomes a variable chart, right? If I say now this is a bivariate chart, right? This bar chart which you're saying it's a bivariate chart, right? Do you agree?
Yes.
Yes, sir.
Okay. Now, if I bring in one more column dimension here, say one more column of males and females, right? And then what I can do is I can in each of these bars I can maybe draw a line and show the different say male and female, male and female, male and female, male and female, right? This is called a stacked bar chart, and this now becomes a multivariate analysis. Got it? You're looking at three dimensions, three columns, three dimensions at the in the one go. Got it? I can also plot this bar graph as a side by side chart, wherein instead of taking this dividing this each bar chart into two different zones, we cut this bar chart and place it at the side of each city X. We have male and female. We place males as one bar, and just adjacent to this, we place females as another bar, right? So in which case this becomes one set, You can have a similar set here, you can have a similar set. So this becomes a side by side bar plot. So whenever we say it's a stacked bar plot or a side by side bar plot, you should understand that it gives you it gives you three variable data, right? Okay. So okay, okay, okay. Now we have covered this bivariate, but let me. So we have seen the visualizations of the uh, bivariate. So when we say bivariate analysis, when we are looking at two variables at a time, right? Two variables at a time. Then we can look at one. So I've already told you what is correlation and covariance, right? Correlation and covariance. Whenever we have two numerical variables, we have two numerical variables, okay. Whenever we have two numerical variables, then we can look at calculate correlation and covariance, or we can plot correlation, which is, how do you plot a correlation? How can you plot a correlation? What do you draw to plot a correlation or covariance?
Scatter plot.
Yeah, yeah, right. So you can always draw a scatter plot to figure out a correlation or covariance between two numerical variables, right? You can draw something called contingency table also, right? You can draw something called contingency table also. Whenever there are two categorical variables which are there, you can draw a contingency table, right? Anyone who understands what is contingency table? So given, okay, so let's look at what does this mean. Okay, now, so I said contingency table between two categorical columns. So smoke and gender. Suppose we take these two columns, smoke and gender, right? And I say, how can you analyze this? How can you analyze this? So they're two categorical variables, right? Yeah. How can you derive some information from this?
How many females are smoker? Then how many males are smoker? Like that way.
Right. Similarly, how many females are non-smoker and how many males are no smoker. Okay?
Yes.
So
Yes.
there are four categories which you said, right? There are
Yes,
four
sir.
possibilities, right? And if you are able to find out
Yes.
the count of each of this possibility, right, that becomes a contingency table,
Yes. Each category having two different
right? If you plot, so yeah, you said female smoker, female non-smoker, male non-smoker. So out of this two columns, these are the four set of combinations which we can find out, right?
Yes, sir. Yes, sir.
Yeah. And if I for these four categories, I just mention the count. That becomes a contingency table, right? That becomes a, so contingency table is always made like this. Is shown as a matrix, right? Is shown as a matrix. Okay. So suppose in this case we say smoker yes no, right? Smoker yes no on the top row, right? And we say male female here, right? And then I say out of that whatever 15 data count, I say five people are male and smoker, right? Male non-smoker, say six people are there who are male non-smoker, right? Similarly, female smoker, female non-smoker. So this count here, once I mention the count, so the contingency table will look like this. One categorical variable and its categories will be shown on one side of it, and the other categorical variable and its categories are shown on the other side, on the say vertical side, right? And then we just plot the count of each. So it could be multiple categories also. It need not be only two categories, right? There could be three categories. There could be two categories in one and three categories in the other, right? So accordingly, you can plot all the uh, uh, counts uh, as a as a and that will give you a contingency table. Okay, is that clear? So contingency table is something which you can draw if as a bivariate analysis uh, parameter, which wherein it can be done only if there are two categorical variables. Right. The other possibilities which exist in this table are so a bivariate, as I told you. So you can have a numerical to numerical. So both the columns are numerical. You will have both the columns as categorical, or one categorical and one numerical, right? So in case of the in case you have one categorical and one uh, numerical, then you have some other parameters, namely t test and f test, right? So t test and f test uh, are a way of uh, finding the relationship, finding the uh, relationship between one numerical variable and one categorical variable, right? Will come to t-test in maybe subsequent classes, but right now just understand if you have to find a relationship or association, right? A relationship or correlation or association, right, between one numerical variable and the other categorical variable, then you use t-test. Okay, and if that if you have to find the association between two categorical variables, right? Like say for example, the one we did, right, smoker and so if I have to find so one way of studying this smoker and gender is that you figure out a contingency table. That is one level of information which you get. Now I'm saying if you have to find the association, so for these, for two numerical variables, you can find a correlation, right? You can find a correlation and you can say whether there's a positive correlation or there's a negative correlation, and how much is the strength. How much is the strength? They are very highly correlated or they are not highly correlated. Uh, I'll come to that. So just coming to correlation back. So correlation, if you calculate the correlation between two numerical variables, it will give you a positive value. It will give you a value between 1 or -1, right? It will give you a value which will be maximum 1 and minimum -1. So -1 to 0 to 1. So any if my correlation value is between 0 and 1, 0 and 1, it is called positive correlation. If my value of correlation is between 0 and -1, then it's called negative correlation. If my value of correlation is 0.9, right, more than 0.9, then we say very high correlation, very high correlation. That means very closely packed positive uh, data set, right, in a positive direction, which means if one column is increasing, other is also increasing. If I say minus 0.9, it means negative high correlation. Again, it is a high correlation, but in the negative side. Say 0 or 0 near 0 would mean that no correlation, right? 0 would mean no correlation. So 0.5 means 0.5 means it's a medium. It's a medium level of correlation, right? Okay. So I said that if I have to if we have to look at the so one one the other thing would be that I want to find out the relationship or find out the association between two categorical columns, right? So for numerical columns we can figure out the correlation, right? And we know whether they're closely associated, whether there's some association or not, right? Similarly, if I say I have to find a correlation between correlation between two categorical variables, right? Correlation is same as association, right? Then I have to plot. Then we have to plot this. We have to do this something called chi-square test. We do something called chi-square test. And if I have to find the relationship between gender and say lung cap, right? If I have to find the relationship between gender and lung cap, wherein lung cap is a numerical column and gender is a categorical column, wherein lung cap lung cap should be your dependent variable, right? So just make a note of this. So when we for doing this t test or f test, if one is that whenever we have to find a relationship between one categorical and one numerical variable, you use t test, right? Or f test, uh, or ANOVA. The three different terms, right? We'll come to that later. But the point is that in all these cases, so you have to make one column. The numerical column has to be dependent variable, right? And the other columns can be anything, can be numerical or categorical or any combination of that. Is this clear?
Yes, sir.
We were at this bivariate analysis, and we said that because your regression and all actually comes out of here only. Okay, whoever has done, I don't know how many have you done. Maybe I remember 3-4 of you. So yeah, this is done before. So usually all this needs to be done before you actually get into machine learning, right? Before you actually start doing analysis of predicting or classifying or clustering, right? This actually needs to be done before. This whole data analysis is something which needs to be done before you actually get into modeling, right? Whoever has done machine learning would understand that it's just an algorithm which you apply, right? There's nothing much you do at that level. So this is something which this takes more of a time, and this is where usually 70% of time goes for data scientists. Okay. So is this clear? For a bivariate analysis, we can do correlation or covariance. We can create a contingency table. We can do t-test and f-test, and we can do chi-square test. And in which case, what is applicable? This is a mathematical way, and the other visual way is that you draw scatter plot, or you draw stacked box plot, or you draw stacked plot. Is this clear? Anyone who has not got whatever has been said till now, please raise it now.
Can you please explain chi-square test?
Chi-square. So chi-square test, right now just understand that chi-square test will be done whenever we have to find the correlation between two categorical variables.
Okay.
Clear? Because you can't draw a scatter diagram for categorical variables, right? Can you draw a scatter plot for a categorical variable?
No, sir.
Yeah.
No,
Sir, no.
So that is where if you have to find a correlation. So now imagine I have to find a relationship. I have to find some sort of association between say smokers and say smokers and say the other was male female, right? So
Gender.
if I have a set of male females and I have a set of smoker habit, yes or no. Now what I have to deduce is whether males are smoking more or females are smoking more, right? How do I do that? That is where chi-square test comes into picture. Okay. So chi-square test is used whenever we have to find a correlation or association between two categorical variables, which could be binary categories or which could be multiple categories. Or ANOVA comes into T-test or F-test, and ANOVA comes into play whenever we have to find a relationship between
More, more than two variables.
categorical variable and numerical variable, right? Yeah, there's a one-way ANOVA and two-way ANOVA. Yeah. But the point is that in this case, a numerical variable has to be a dependent variable. You can't have a ANOVA for a dependent variable which is categorical. Okay. See what is happening. What are we trying to do, right? This is so I said now. Given a data set, you need to find a relationship between dependent and independent variables, right? You agree to that? End of the day, that's our objective is, right? Whatever you're doing.
Yes.
Now, wherein before actually you say that, say for example, uh, say in this case, in this data set, if I have to say if I have to predict for lung cap, right? If I have to predict lung cap given age, height, smoke, and gender, right? Now, how do I know? How do I know that smoke has an impact on lung cap, right? Before actually getting into, assuming I've got this data fresh, right? I'm seeing it for the first time, or now before we get into higher algorithms and all, we'll have to understand whether, say, smoke has an impact on lung cap or not, right? So is this smoke a valid uh, uh, valid variable for a lung cap, right? Or it has an impact. Is the data showing that it has an impact? Then only we'll consider smoke as a independent variable for figuring out lung cap, right? So that whether it has impact, whether they are associated or not, is something which we have to figure out. And that is what, in case it is a set of one categorical and one numerical variable, we get into ANOVA, right? If there are two categorical variables, then we get into chi-square test. Is that clear? Anyone who is not clear on this point?
Clear, sir.
And if it is two numerical variables, we calculate correlation. So I want to hear from others also. Are we clear? Mirza, Akshita, okay, Zoya. Because this is important. If this is clear, then things will become clear for you. Okay. Now the third thing comes. Now the next step is multivariate analysis. Multivariate analysis, right? Wherein we are talking of one more than two uh, more than two columns, right? Wherein, so there again, so for a multivariate analysis, so in this example, I take age, height, and say lung cap, for example, right? There are three variables. Now this becomes a multivariate analysis. For this again, we can create a correlation plot. Now correlation plot can be, now there are multiple correlation plots which we can plot here. One is between age and height, right? One is between age and lung cap, and the third is between height and lung cap, right? Are we clear on this? So this becomes a
Yes, sir.
multivariate analysis. So multivariate analysis means that we are talking of more than two columns, and those two columns here in the example, I repeat. Now I take age, height, and lung cap as three variables, and I can find a correlation between these three. Now correlation would be of, I'll get three correlation. I can create three correlation plots from these three columns. One is between age and height, other is between age and lung cap, and height and age. So I can have these three correlations figured out. Okay. Is it clear?
Yes, sir.
Okay. And and if I have to find a relationship between, say, lung cap right, as a variable, and gender and height, for example, right? Height, gender, and lung cap. Okay, wherein lung cap is my dependent variable. So that is a condition which I have to put. Now, in which case, what do? I figure out ANOVA. I figure out ANOVA. We'll do something called ANOVA. We do something called ANOVA, which gives us the relationship between lung cap and height and say gender, or any of these set. So if these four columns I have to see with respect to lung cap, I actually draw a ANOVA. I figure out a ANOVA, something called ANOVA, which is analysis of variance, right? Which is analysis of variance, full form ANOVA. So I just see how these four variables are impacting the dependent variable, how these four independent variables are impacting the, and if I'm able to quantify that, if I'm able to quantify that relationship, right, if that becomes a regression, right, that becomes regression. So how many of you have done machine learning? Okay, anyway. So are you getting this? Are you, so one is I'm just, as of now, what we are saying is, yeah, okay. So what we are saying here is that in correlation we are just finding whether the relationship is positive. In covariance we are seeing the relationship is positive or negative. In correlation we are actually seeing the strength of that relationship, right? And if I'm able to quantify that relationship, right, that becomes a regression. If I'm able to quantify, if I can say lung cap is equal to say 0.5 times age plus 0.7 times height plus 0.1 times smoke minus 0.2 times gender is equal to lung cap, right? If I'm able to find these coefficients, right? If I'm able to find these coefficients, if I find this if we are able to find this equation, that is what is regression, and that is where once we have this equation, you are able to do prediction, right? Is it making sense to you? So before you do regression, you'll have to do correlation, you'll have to do covariance, you'll have to do chi-square test, you'll have to do t-test. Okay?
Yes, sir.
Okay, fine. Okay. Okay, okay, just to show you this, okay. Okay. So covariance, as I told you, it gives you the direction, right? If you calculate a covariance, it will, so this a direction wherein if you move towards right and you get a corresponding figure, corresponding y, which is moving from low to high, that is becomes a positive covariance, and if it's reverse, then it is negative covariance. And so something like, say, if the data, if your r, if you plot these points and your data is like this, it's quite spread out, right, and it's in a positive direction. So this is a positive correlation, and this is almost equal to 0.4. So mathematically, this will come out to be 0.4. If the data is like this, if there's no pattern, it's horizontal, there's no pattern you can define, right? Then, or no direction, in fact, no direction you can figure out, then it has no correlation. And this is a negative correlation. This is negative correlation of value minus 0.4. Okay. Okay. So, how many of you are familiar with R? So I can demonstrate this few things to you in R. How many of you are familiar? Anyone who has done R? Okay, so maybe okay, so maybe whoever has it can can maybe do it with me, I can or maybe note down the commands. For the others who have not who okay, just hang on. Yeah. For the others who they can quickly actually do this with me, because that will help. We'll be using this. So you don't need to. So just go to this link quickly and download R. So there are two R from that there. Are you doing this, or you want to do it later? Okay, maybe I okay. So let's not. I think we don't have much time. So आप ऐसा करो, ये आप link note कर लो, right? So there to. So let me explain. So you have to download. You have to go to this location. You will find R on the download R, right? So you have to download that and install that, right? And then once you have installed that, so this is the first step which you have to do, take complete till installation. And then you go to this link www.rstudio.com and download RStudio on that. Download RStudio and install RStudio, right? So we'll be working on RStudio. R is a base software, right? But interface is RStudio. Okay, interface is RStudio. Just note this down and uh, uh, then just be ready with this if you want to do it yourself, right? Or even if you don't do it, it's up to you. There's no, if you don't want to do it, I just want to use it as a demo, so I'm using it. But if you want to do it yourself, then you can do it. Then you can, so whatever, and note down whatever I'm telling, showing, so that you are familiar with this. Okay, so let me show you how our whoever has not worked. So we have this data set. Okay, let me. Okay, are you able to see this screen? My screen of R.
No, sir.
Okay.
No, sir.
Okay, fine. So if once you have installed R and R Studio both, and you click on R, you will be able to get this screen, a screen like this on your desktop or laptop, and wherein, okay, doesn't matter. Whoever doesn't have R, they don't need to bother, because I am just using it as a demo for you. You don't need to understand the commands also. And so just to show you that we have this data set which I have. Okay, and I'll show you how. I'll show you. Okay. Now I have read this data in R, which has this columns X, then there is a sex column, then there's a weight column, then there is height column, then there's a repeat weight and repeat height. So maybe the weight, height and weight were repeated measurements, right? So for example, this is a person of age. So age X corresponds to age. No, not age. Maybe I don't know, 29th day, or so X is just maybe a core, maybe a serial number of a particular entry. X is just a serial number of this entry. Then there's a sex column. Then there's a weight column, height, repeat weight, and repeat height, right? Now, sex is a categorical column, right? And the rest of them are the uh, numerical columns. So, so just okay. So what I've just done is I've removed the other columns. I'm retaining only these three columns: sex, weight, and height. Right? Sex, weight, and height. Now, what is that I can do with say height? So if I have to analyze say height, for example, then what is all that I can do? What all can I do with height column, for example? If I have to statistically analyze height column, what is that you would like to understand? So there are about 199 rows, 199 rows of the data, right? And these are the female. There's a uh, male female column. There's a weight column and there's a height column. Now I'm saying ki, so given this information of 199 records, what is that you want to analyze? What is that you would like to? Okay, so we said mean, right? We said univariate analysis, right? So we can simply do mean of height, right? Mean of height. So mean of height is coming out to be 170.58. Okay, median of height. So we can find median of height, right? Median of height 170. Okay, so 170 would mean that if I arrange these heights in a ascending order or descending order, at the 50th position, I'll see the value 170, 170. Okay. Similarly, maximum height. Right. So this is the maximum height, right? You'll have to see this. So basically, this is the code which I have, and on this window, which is console window, there you are seeing the output. We are seeing the output, and these are the columns. These are the next other two windows. So R as interface has four windows: 1, 2, 3, and 4. Okay. Minimum height. So what is the minimum value? MIN height 148. Okay. So now I know that my minimum height is 148 centimeter and maximum height is 197 centimeter. My median is 170.58. Sorry, mean is 170.58 and median is 170. Quantile, right? What is the value at 25th position? 164. At what is the value at 10th position? 160. What is the value of at 90th position? 180. What is the value at first position? 151.96. Okay. Similarly, we can find this. So this we can find range, for example, range. So range is the difference is a maximum value and minimum value. Maximum value and minimum value, right? Then you have IQR. IQR. That's a difference between Q3 and Q1. Right? Similarly, variance. This is variance 80.08 for the height. Now, if I have to find the variance for say weight, for example, so let's see. I just copy this. So 169.20. So weight, which means weight the data is more spread out, right? Weight the data is more spread out, and even otherwise the value of weight would be more, right, than the height. Okay. ST, standard deviation. Standard deviation is of height is the root 80.08 का root करेंगे 8.9, right? Okay. Okay. Now we are saying univariate visualizations. So this is a plot, a simple plot, right? Plot would mean that I'm just plotting height. We're just plotting height, and this is just index. Okay, so this plot, if you see, this is a univariate plot. Do you agree with me on the right side?
Yes, sir.
Yeah, so this is just index. This is 0 to 200 mean, 0 to 200. This is a zeroth value. This is first value. This is second value, third value, fourth value, right? This is just that value plotted on the y-axis. This is a univariate plot. Okay, I have plotted my 199 observations like this. Okay, so which means 100th observation is at this level. Then your bar plot. Okay, so this is again just giving us the value. So each bar corresponds to each value. So from 0 to 1, 1 to 199, all values are plotted with respect to their values, with respect to their values. Okay, so there are 199 bars here, 199 bars here. Okay, so this is again a univariate plot. Then box plot. So I'm plotting a box plot for height. Okay, this is a box plot. Now this is what I told you, right? So this is the black line in between is a median. So median is what? If you extrapolate this line on the y-axis, this becomes 170 point something, right? This is a median, right? Are you with me? Are you clear on this median?
Yes, sir.
Similarly, this is Q3. Q3 is less than 180 something, yeah. Q3. Q3 actually हमारे यहाँ पे कितना आया है? Q3 हमने कैलकुलेट नहीं किया, लेकिन Q1 is 164, right? Q1 is 164, okay? Q1, Q3, Q2, and this is your maximum value, and this is the minimum value. There is no outlier in this data, so you are not seeing any outlier. Is it clear?
Yes, sir.
So similar, so you can have multiple bar plots. अगर इसको category के against में plot करूँ, suppose male, female, right? Then you can have two plots here, wherein for male is one, for female is other. Similarly, now histogram. So we are plotting histogram for height, HIST, histogram for height column. So this is how it's looking like. This is how it's. This is bit right skewed, right? This is bit right skewed data. Histogram of height. Okay. This is if I draw a line joining the middle of each bar, then I get a plot like this, right? Now you see it's a right skewed data. Are you able to figure out that there's some right skew, not very high right skew, but some right skew?
Yes, sir.
Okay. Okay. So and this is showing you a frequency. This is showing you the frequency, say 160 to 100 between 160 and 165 height. There are maximum. So maximum number of people in the data have the height between 160 and 165 centimeter. Okay, there are very few people who have a height beyond 190 centimeter, for example, right? And very few which are less than 150. Okay. Okay. Then you can also we can actually mathematically calculate skewness. So 0.20, this data has a skewness of 0.20. Okay, this data has a kurtosis of minus 0.3. Okay, less than 3. Okay, which is bit flatter, right? Bit flat. It's not that peaked. Okay. Okay. Now I'm getting into bivariate analysis, wherein we are finding a correlation between height and weight, which are two numerical columns. So correlation is coming out to be 0.78. This is a mathematical calculation. Okay. covariance is plus 91, but in covariance we don't go by the value. We don't see the value. We just see the sign. It's a positive number, right? For covariance, the number is positive, plus 91. So it is a positive trend. It is a positive correlation. Even otherwise, the correlation is between 0 and 1. The correlation which you see is between 0 and 1, so which is indicating that it is a positive correlation. In fact, you don't need to calculate covariance here. Correlation directly gives you whether it's a positive correlation, negative, and it also gives you the value, strength of that correlation. Okay. Okay. Now this plot. Plot, it can be called scatter plot or it can be called a correlation plot. So plot. So this is the plot. Now on the right side, which you see is a correlation plot or a scatter plot. Right? This sort of density. Now you see this is a positive, right? This is a positive trend. This is a positive direction, right? So which is corroborated by the correlation and covariance values which we have got. It's a positive correlation, and 0.78 correlation looks like this, wherein it's densely packed. It's comparatively densely packed in a positive direction. Okay, is this clear? Scatter plot.
Yes, sir.
And here you are plotting two different variables, height and weight. Here you are plotting height and weight, right? Height and weight. So any two numerical columns can be plotted like this, and this is called a scatter plot. Okay. So actually, yeah. So this is a same plot. We have just plotted a line to that, just to show you that it's a positive direction, and it's bit denser than 0.4, which you saw. Okay. Okay. Now, so now whatever I'll do will be on this data set, which is a lung cap data set, right? Lung cap, age, height, smoke, gender, right? Cesarean is one other column which we have not we have not seen, but anyway, that's not a problem. So lung cap, right? Now here I'll show you how you plot a contingency plot. How does it look like? So I'm drawing a contingency plot between smoke and gender. Smoke and gender. Right? Okay. Okay. So this is how a contingency plot looks like, right? On the left side. So here is, you can see a contingency plot. It's between smoke and gender. So there are two columns, right? And gender male and male, and smoke is gender. So there are 314, right, smoking, and there are 334 males who are not smoking, right? No female, smoke no female, 314, smoke no male, 334, smoke yes female, 44, smoke yes male, 33. Okay, so you'll observe which category in smoking. If smoke is yes, which is who smokes more as per this data? Who smokes more
Female.
as per this data? Female, right? Yeah. Okay. So this is what is a contingency plot. We can have multiple categories, right? We can have multiple categories in each of these categorical variables, and this will give you multiple. Now let's see. Now we'll plot a stacked bar plot. Yeah. So for this data, we have created a bar plot. wherein we are saying that these values 314 and 44 and 3, 3, 4 and 33 are plotted here. Okay, this is a side by side, you can say, bar plot. Okay. Okay. Yeah. Let's look at. Yes, it. Yeah. Okay. Okay. Now, so this is what you're seeing now is a multi-variate analysis. It's a multi-correlation plot, right? Now, what we have done is I have taken all these columns: x, sex, weight, height, repeat weight, and repeat height, right? And I have created corresponding correlation plots for all the combinations which are possible, right? So in R, there's a function called pairs which gives you this facility. Now, this is what is a multivariate analysis now, wherein we are trying to see the correlation between each variable with the respective variable. So how do you read this is now x. So x and sex, x and sex. So this is a plot. This is a plot x and sex. Similarly, this left hand plot is also x and sex. Okay. Now typically weight and height would be quite correlated. Weight and height, weight and height. So this is, you see, this corresponds to weight and height. Right? It's a positive, very high positive correlation, right? Very high positive correlation. So between weight and height, in the normal course also you will understand that there will be a correlation, right? The person who has a higher weight would likely to have a high height also, right? A person who has a good height, has a more height, would is likely to have a more weight. Right? A person who has low height would have less weight. Okay, so this is, and it is plotted for everything, right? Weight, height. Now, if we have to see and repeat weight and repeat height, there's also correlation, right? Repeat height and repeat weight are also positively correlated, right? Are also positive. There's no correlation between, say, repeat height and x, right? X is just a number. X is just a count. It's just a serial number, right? X is just a serial number. So here you see that the graph is coming out to be like this. That there is no correlation, right? Which means we don't need X is something which is not required. Is a redundant, is a data which is not required. Okay. Yeah. Okay, so what we have done is we have done univariate analysis, we have done bivariate analysis, and we have done multivariate analysis, and we have seen what are the various mathematical parameters or mathematical values which gives us information about the data, right? Whether it's a univariate, bivariate, or multivariate, and there are different plots which help us give information about the data, right? Similar, like say correlation, for example, we can find mathematically also, and we can also find by way of plot also, right? Similarly, uh, uh, say box plot, we can find median mathematically also. We can find median by box plot also, right? We can find quantile, minimum, maximum all through box plot, right? Similarly, histogram gives you the distribution. It tells you the skew, positive or kurtosis. So skewness and kurtosis can be found mathematically also, and skewness and kurtosis can be visually seen by plotting a histogram. Okay. Okay. So you can actually, so these uh, this visualization or this statistical calculation can also be done in Python. It can also be done in Excel. It can also be done in Excel, right? It can be so just because we're doing some language, so I've shown it to you in R. You can, if anyone wants to explore it in Python, he can very well do it on their own, wherein their libraries in stat library, statistical library in Python, which allows you to do some of these functions. Right? May not be all, but few of them for sure. And whoever are interested can maybe for practice they can download R and R Studio and they can practice. So there's a lot of they can practice on their own on R by creating this. But essentially, I wanted to show you that this is there are the different uh, ways you can analyze the data. Okay. So any question for today? Because so we've covered whatever I wanted to in the initial phase. So if you have any questions on any doubt in today or in the last session, you can ask me.
So can we get this PPT and the
Yeah, that
recording of today's session?
yeah that uh, that okay, that I'll give it to you in the next session, or I'll get it arranged. So I think we are also recording this video. They're also recording this video, so you can maybe. I think you should. I'm not sure. You should also get access to that. I'll arrange so you'll get it. You will get this PPT also.
Sure, sir. Thank you.
Any other question or anything which you want to, any comment which you want to make, or anything which you want to share? You're finding it relevant?
Yes, sir.
Okay. Any question you have? Uh, any doubt? If you go through any statistics book, it will be very mathematical, right? Now, I am trying to show you the practical way. Yeah, if there's no doubt, then we close. Kindly confirm. If there's no question, further question. Okay. Okay. Yeah, great. Then we close, right? Yeah. Okay. Bye then. Bye everyone.